Okay, this is MAT 175 and this is lesson 6, section 3.4, quadratic models, building quadratic functions from data. Alright, so first thing we're going to do is we're going to look at this first problem. And it says the marketing department at Widgets Incorporated found that when certain widgets were sold at a price P dollars per unit, the number, we'll use X for the number of widgets sold is given by the demand equation, where the number of widgets is equal to 1500 minus 30 times P for price. Find a model that expresses the revenue R as a function of price P. Alright, and then we're going to want to find the domain. Price should be used to maximize revenue, and the price charged what if this price is charged, what is the maximum revenue? Okay, so first of all, revenue, the equation for revenue is the number of items times the price. Since the number of items equation is 1500 minus 30p, we substitute 1500 minus 30p in for X. So it's 1500 minus 30p times p. And so we have to distribute that p, and we switched places here, made this minus 30p squared plus 1500p. So now we have our revenue equation. Now what we want to do is we want to find the domain. So we take this revenue, and what we do is we take the, so now we want to find part B, what is the domain? So we take the number of widgets equation and we set it to greater than or equal to 0, and we solve for it. And so we went ahead and subtracted 1500 to both sides and divide by negative 30, switch the inequality, and we get P, the price, is less than or equal to 50. So therefore the domain, now we've been using interval notation, and they're using set notation here. For us, it would be open at 0 and then P, and then close bracket at 50, or open at 0 comma 50 close bracket. But here we're using set notation for the domain. Okay, so that's part B. Alright, so now we want to know what is the unit price should be used to maximize the revenue. And what we do here is we use the equation for the axis of symmetry. Now if we go to the next, here's our graph. Now this is the graph for our revenue equation. The axis of symmetry splits the parabola in half, right at where that vertex is at, where it peaks out. So this equation is that line right there, that negative b over 2a. So anytime we want to find the maximum, point, we use this negative b over 2a. So in this case, the b is 1500. A is the negative 30. B is the coefficient of in this case, P, 1500. There is no C here. C is 0. So here's our A for the P squared. Here's our B for P. There is no C. So we put in 1500 in for B. Here's our negative, and then 2 over 2, and then negative 30 is our A. Simplify that, we get $25. So what that's saying is that, skip over to here, at $25, which is right here, we're going to get a maximum value here, profit, revenue. We're going to get a maximum revenue here. So if we charge at $25, we're going to get maximum revenue here. And let's see what that is. So we have our revenue equation, and we're going to substitute R of P in there equals to negative 30 P squared plus 15P. And we're going to put this $25 in here for P. And so this is 25 squared times negative 30 plus 1500 times 25. And we get $18,750 in revenue charged at $25 price per widget. Okay, now we want to know how many units are sold at price P. Well, here's our demand equation. The number of units is 1500 minus 30P. That's the same equation we had here. And so here's our revenue equation. And so what we're going to do here is we want to see how many units are sold at $25. Well, we substitute 25 in here, $25 per unit, and how many widgets can we sell? And so we get 750 widgets at $25, and that's where and we get that maximum revenue of $18,750. Okay, and so we are going to graph this equation here, and that's what this is. This is revenue, this is price. Down here, X is price, Y is the revenue. What price should Widgets Incorporated charge to collect at least $12,000 in revenue? Well, here's 12,000. Okay, that's the Y value. So we have to take this 12,000 and substitute it in for R of X. And you can see if we draw a line at 12,000, there's going to be two places where we'll get a revenue of $12,000. So we substitute 12,000 in for R of X, and we get into our equation. Well, we have to apply minus 12,000 to both sides. Or in this case, what they did was they added 30P squared and subtracted 1500, left 12,000 on that side. But you could subtract 12,000 and then divide everything by negative 1. Either way, you get the same thing. They factored out the common factor. You could also divide it out, get rid of it completely, and then from here we factor. And factors of 40 are negative 10, P minus 10 and P minus 40. So we get P equals to 10 and P equals 40. So at price $10 per widget, we get a revenue of 12,000, and also a price at $40. We go move up here, and that's also where we get $12,000 revenue. Okay, and so the company should charge between $10 and $40 to earn at least $12,000 in revenue. If they want exactly 12,000, they would pick those 2 points. But if they want at least that, at least 12,000, then they would get, see here, they would be like 15, they'd be higher. And so as you get further in between these two, then it comes up higher and higher. So this is 12,000, and this is at least 12,000 up here. Okay, here we have a farmer's yard. Looks like a little plot of land. And it has 1,600 yards of fence. So 1,600 yards of fence, that's going to be perimeter, because it's the outer perimeter of the plot of land. What are the dimensions of the rectangle that encloses the most area? So the first thing you want to think of is area equation. Well, what's area? Well, area is length times width. Well, X is the length, W is the width. But we don't have, the 1,600 is not part of area. It's part of perimeter. So we have to plug the 1600 into the perimeter equation. We can't plug it into the area because it's not area. So from here, we can just divide everything by 2. And we get x plus w equals 1600, and then subtract x to both sides. So we get width equals to 800 minus x. And from here, we can go ahead and substitute that into our area equation. So w equals to 800 minus x. Take that, substitute that into w for our area equation. And then from there, we can go ahead and distribute the x, and we get negative x squared equals to 800x. Okay, and then from here, we can go ahead, now we have our, again, it's shaped like a parabola. So we need that peak. So we have to take that x equals to negative b over 2a. Well, where is the b? You should have said 800. Well, where's the a? That's negative 1. And so we get negative 2, we get 800 over negative 2, but you got a negative here and a negative here, so the negatives cancel. And you just get a positive 400. So that's our maximum length, but we have to find the width. So you can plug that back into either equation to find the width. I believe they use the perimeter equation. So to find the width, you just take the 400, put it into x, because that's what this is here, and we get 400. So the length is 400 and the width is 400, and that's our maximum. That's our dimensions to get our maximum area. Okay. Now let's take a look at the next problem. We have a Golden Gate Bridge and it has a suspension bridge on it. And so here it is. The bridge extends up from the ground 746 feet. The towers are that tall, and they're 4,200 feet apart. Now notice they split the bridge in half and made it 2,100 and 2,100, and there's a reason for that. Okay, and we'll go over that in a minute. The bridge is suspended from 2 huge cables more than 3 feet in diameter, 90 feet wide. Roadway is 220 feet above the water. Well, here's 200. Here's the ground. Here's 220 feet. So here's the bridge. It's 220 feet. But we want this height right here because that directly affects the cable. So we have to subtract 746 minus 200, and that's where the 526 comes in. So this height is 526 feet. So we split this bridge because half of it, if we were to look at it as an XY axis, this would be, X would be 2,100, and that's where this comes in. The Y is 526, so that's where this comes in here. So we could look at that as like a coordinate point. Well, we need an equation. We know it's a parabola, and the basic equation for a parabola is y equals to ax squared. Well, a, later on we'll learn that a gives us either more what we call steeper or vertical stretching or flatter parabola, or what we call vertical compression. Well, we need to know what the a is. So what we do is we take 2,100, substitute it into the x, 526, substitute it into the y. Okay, and that's what this is. And then we can solve for a. So we divide both sides by 2,100, parentheses squared. And they just left it that way. They didn't square the denominator. And so now you can substitute that back in for a. And so now a is 526 over 2,100 squared, x squared. Okay, now from here, we can go ahead and now it asks, find the height of the cable at a distance 1,000 feet from the center. So here's the center. We want to go 1,000 feet out. We want to know what is this, how high up off the bridge is that cable. So you substitute in 1,000 in for x, square it, multiply it times 526, divide by 2,100 squared, and we get 119.3 feet. And that's our answer. Okay, now we're going to look at building quadratic models. Now we did this similar to this with linear, and so this is more of a quadratic model. And so this is what a quadratic model looks like, an x squared. This is a positive x squared, and this would be a negative x squared. And so we have some data here. And I went ahead and entered the data into my calculator. And so here's my calculator. Now what you want to do is you want to go to second. To clear the list, you would go to second in memory and then clear all lists, 4, and then hit enter. I'm not going to do that because I have this table already entered, so I'm not going to hit enter here, 4 and then enter. But you would if you want to clear your list. Alright, so now what we want to do is we want to enter this data. So we go to stat, and then edit. So we're just going to hit enter. And there's plot 1 at 0. Here's list 1, here's list 2. And so this is 0, list 1 is 0, list 2 is 4. And here we go 0, 4. And then 0, 6, and here's 0, 6, and 5, 10, and 5, 10, and so on. And so I've already entered this data in, so you would need to enter all that. Okay, now now I tried to go to graph it, I tried to go to Z standard. Here's zoom standard. And so if I did that, see if I went to 6, see it doesn't show it because this other line here, it doesn't show it. So we just want the first quadrant. So you can go to window, and since this is going from 0, the x value is going from 0 to it goes on to 40. This goes on here to 40. Here's 40. We're going to go x min is 0, and then x max. We're going to go a little bit further. We're going to go to 50. And then the same. And now here, the y values, they go to 19. Well, we're going to go 0 for y, starts at 0, and we're going to go to, goes up to 19. We're going to go to, you want to go a little bit further. That was y min. I'm on 0 there. So we'll delete that. And then y max, we're going to go to 25. Go a little bit further than 19 so we can see the whole thing. And so I went ahead and so here we are. And so now when we go to graph, there it is. And you can see that it's showing a parabola. So we want the linear regression for a parabola. So we go to stat, and we go to calc. So we have to hit the right arrow. And instead of linear regression, we're going to hit quadratic equation, 5. And we're going to go to to second and L1, comma, second and L2, and hit enter. And there's our quadratic regression. The A is a negative 0.017 x squared plus 1.0765x plus 3.89 for the C. But now what we want to do is we want to get that, we want to take that and impose it into our graph. So from here, we go to y equals. And we're going to hit vars, and we're going to go to 5 for statistics, and then we want EQ, so we have to hit right arrow, and then right arrow again until the EQ is highlighted, and there's one regression equation. Hit enter. And there's our regression equation in the y equals, and we can see that that's in our graph. There it is. Okay, so we did that on our calculator. So now we can continue with that. So a farmer's, so in that case, farmer collected data. Here's our table, which shows crop yield. So from here, we wanted to use the function in part B to determine the optimal amount of fertilizer to apply. And so that's where we went ahead and found our negative B over 2A. Where is it? Okay, so once we get that, right, at that point, use a graphing utility to find the quadratic function that best fits the data. And that's our quadratic function right there. So use the function part B to determine the optimal amount of fertilizer to apply. And from there, the farmer has collected data in table 3, which shows the crop yields various amounts of fertilizer. Draw the quadratic function best fit. Okay, so from this point, we want, so here's our quadratic, graphing utility to find the quadratic function of best fit data. Here it is right here. That's our equation. Use the function in part B to determine the optimal amount of fertilizer to apply. So you could use that negative B over 2A here. And that would be your optimal, determine the optimal amount of fertilizer to apply. So from there, we can go ahead and we've got our equation y of x is black. We've got our equation y of x is equal to a negative 0.0171 x squared plus 1.0765x plus 3.8939. So we would use that x is equal to negative b over 2a. And so b is 1.0765 over 2 times a, which is a negative 0.0171. And so the negatives cancel. And so we would get, let's see what that would look like on the calculator. So that would be 1.071 0.0765 over 2 times 0.0171. And get out of the graph. So we put in here 1.0765 divided by, and I'm going to use parentheses, 2 times 0.0171. And we get 31, we'll call that 31.5. So that would be right about here. 31.5 would be your maximum. And our yield, our maximum yield, would be, so 31 is a little bit past, so we're looking at somewhere around 21, 22 bushels for maximum yield at roughly 31.5 pounds of fertilizer will give us a maximum yield of about 21, 22 bushels. Okay. Use the function in part B to predict the crop yield when the optimum amount of fertilizer is applied. So basically, what we have to do is we have to take this equation and and so we know we're going to get, we said that was 31.5. We're going to say 31, we're going to call it 31.5. And so we're saying this is 31.5 here. And so we're going to put in here y of 31.5. We're going to plug that into our equation and see what we get. And so that's going to be negative 0.0171. We're going to put 31.5 squared plus 1.0765 times, again, put 31.5 in for x, plus 3.8939. And we get our equation from there. Go ahead and substitute that into our calculator. So let's see what that looks like. So here it is. We're going to substitute that in. So after we get the negative, we get the 1.0765 over negative b over 2a, we get 31.47. So if we store that into x and hit enter. Now we go ahead and we put in that negative 0.0171, and then we'll put in the x squared plus 1.0765 and then x plus the 3.8939. So that's what this is here. So in other words, you can put the 31.5 directly from the calculator into x. And then from there, we are using the quadratic equation, but we're putting the 31.5 into x here into our equation, since we're stored the 31.47 in for x. Now all we have to do is hit enter, and we get 20.8. So what this is saying is that at a maximum, we want to know, we want to use the function in part B to determine the optimal amount of fertilizer to apply. So we said that 31.5 roughly was our optimum amount of fertilizer, and we said before that it was going to be around 21 to 22. Well, after substituting in 31.47, we used the exact number, we got 20.83. So that's rounded up to 21. So that's pretty close to what we had. What we said was in accordance with the chart. So that worked out pretty close to using our model as we did with using our data, and that would be right here at we said 31.5, that would be about here, okay, with the maximum yield. All right, and we have our quadratic function, and we showed that